Welcome to the Emergency Management Institute's refresher course for radiological monitors. This course is offered on videotape because emergency management professionals like you cannot always get to classroom locations. It is designed to ensure that you have the information and skills needed to respond safely and react correctly to incidents involving radioactive material. We will review ionizing radiation and its effects, procedures to be followed in a radiation emergency, radiological instrumentation, and monitoring techniques. Because we want you to get the most out of this learning experience, there are some items you should have close by as you complete this course. In addition to the television monitor, VCR, and this videotape, you will need the course student manual and a set of radiological instruments, including a CDV 700 survey meter, a CDV 715 survey meter, a CDV 138 dosimeter, a CDV 742 dosimeter, a CDV 750 dosimeter charger, and at least 2 D-cell batteries. It is also important to have a copy of your local or state radiological protection annex and standard operating procedures for radiological accident response. The student manual from the Fundamentals course for Radiological Monitors, SM320, and the most recent copy of the Emergency Response Guidebook published by the U.S. Department of Transportation will provide additional reference material but are not necessary to complete this course. From this list of course materials and equipment, you probably have guessed that this will be an active learning experience for you. The course includes 2 types of activities. One is the written exercises you will complete in the course student manual. The other type of activity is radiological instrument exercises that require the use of the equipment you have nearby. Let's take a minute to look at the student manual. Please pick it up and follow along in the contents. Those of you who have taken other FEMA courses will be familiar with the layout of the manual. The opening pages include a table of contents, a foreword about videotape training, the course goal and objectives, and a list of the course requirements and equipment. A discussion about the use of the manual completes the opening section. If you have not read the opening section of the student manual, pause the tape now and do so. Resume viewing the tape when you are finished. The next 5 modules follow the organization of the videotape. You are now viewing Module 1, the Introduction. It covers the course format and reviews some important ideas about radiological hazard analysis. Module 2 is titled Review of Basic Concepts. It addresses basic radiological protection principles, radiological hazard assessment, monitoring techniques, and protective actions. Module 3, called Radiological Monitoring Instruments, covers radiological monitoring, instrument proficiency, and how to determine radiation exposure rates. Module 4, Radiation Accident Vignettes, presents hypothetical and real-life scenarios. You are asked to apply important course concepts in answering response-related questions. Module 5, the course summary, reviews course objectives and highlights. Each of the modules in the student manual begins with a cover page or pages outlining the objectives, scope, references, and necessary equipment. The subsequent pages take a variety of forms, such as charts to be completed, questions to be answered, summarized content information, or space for note-taking. When it is time for you to participate in a course activity, verbal instructions will direct you to the appropriate page in the student manual and describe the requirements. You should then pause the videotape and complete the activity. When you are finished, resume viewing the tape. As you complete course activities, remember that this course intends to stimulate your thinking about the radiological environment you live in and the response that might be required in a radiation emergency. Application questions and exercises are designed to prompt your input on issues concerning local radiological hazards and your local and state radiological response procedures. Any questions or issues raised in this course should be discussed with your local emergency program manager or state radiation authority. Please do not let your questions go unanswered or your thoughts unheard. They are important. Let's begin by reviewing the concept of radiological hazard analysis. Radioactive material can be found virtually everywhere in the air, soil, rocks, and mountains. It can even be found in the wells and basements of our own homes. But the health hazard presented by naturally occurring radioactivity is usually relatively insignificant. Radioactive material that has been mined, refined, and processed into products also can be found practically everywhere. It is this material that you may confront if an accident or incident occurs while it is being produced, used, stored, transported, or disposed of. The risks from these radioactive materials cover a broad scope, ranging from products that pose no immediate danger from direct exposure to materials so radioactive that an exposure of just a few seconds can cause painful injuries or death. Let's look at the uses of radioactive material and put them into some broad categories. Medical and research uses include diagnostic testing, therapy, and research at medical schools, hospitals, and universities. A few examples of industrial uses are radiography for quality control of pipes and other welding, well logging, and industrial static eliminators. Mobile nuclear facilities or devices are transportable reactors. They may be used as portable power sources for nuclear submarines, automatic weather stations, satellites, and communications relay points. Fixed nuclear facilities include nuclear reactors and reprocessing plants. Radioactive materials also are used in the fabrication, transportation, and storage of nuclear weapons. Accidents involving radioactive material may occur during any of 4 stages: production, transportation, use, or storage. The production stage includes mining, production, fabrication, and related activities. Transportation involves the movement of radioactive material from one point to another during its life cycle. Radioactive material often is moved from where it is fabricated to where it will be utilized, and again after it has been depleted. The chance of an accident is highest during the transportation stage. Use includes all of the applications of radioactive material, such as medical diagnostic tests or industrial radiography for quality control. Fortunately, once radioactive material is in the hands of the personnel who will be using it, the probability of an incident is very low. Storage can occur at any point during a radioactive material's life cycle. For example, the radioactive training source sets you may be familiar with are stored in lead containers, sometimes called pigs. Spent nuclear fuel rods are buried in underground storage containers. Do you know what potential radiological hazards exist in your community? The first course activity is intended to stimulate your thinking about local production, transportation, use, and/or storage of radioactive material. You may have conducted previous radiological hazard analyses, but we encourage you to take this opportunity to consider possible changes in your local environment. New hazards may recently have been added, while others may have been eliminated. On page 4 in your student manual is a chart where you can record your answers. If, after you are finished, you feel your chart is incomplete and want to know more, contact your emergency program manager. When you have completed the analysis, restart the tape. Module 2. Module 1 set the scene and laid the groundwork for the remainder of the course. Module 2 begins with a review of the structure and function of the local radiological protection system. The remainder of the module will refresh your memory on some other very important topics: basic radiation protection principles, radiological hazard assessment, monitoring techniques, and protective actions. As a radiological monitor, you operate within an organizational structure called the Radiological Protection System, or RPS. The mission of the RPS is to provide first responder support to radiation incidents. In these situations, state and/or federal expertise and resources usually will be available to support local efforts. Each state has designated a qualified radiation authority to deal with radiation incidents and accidents. However, the state radiation authority normally will not be the first one on the scene of a radiation accident. That is why local jurisdictions need to have first responders trained to deal with the immediate radiation hazards. To be able to fulfill its mission, the RPS must maintain operational readiness in 4 areas: self-protection monitoring, to assess the radiation environment of personnel who must conduct emergency operations in a radiation environment; monitoring, reporting, and assessment, for determining the extent and magnitude of the radiological hazard in the jurisdiction; radiological decontamination, to reduce the radiation levels from radioactive contamination; and shelter monitoring, to assess the radiation environment for shelterees. The RPS operates within the local emergency management system, which is headed by the emergency program manager. The local RPS includes a radiological response team, or RRT, whose members serve as a team of radiological responders for incident command. RRT members are drawn from emergency services, essential services such as public works, and vital facilities such as public utilities and hospitals. They serve their respective organizations and are coordinated as a team by the local emergency program manager. The key element of the radiological protection system is the radiological monitor, or RM cadre. This is where you fit in. You and other RMs are trained to perform basic radiological monitor functions and to report to your RRT. The radiological protection system relies on trained personnel, and the system must work right the first time it is needed. To assure that it will work, it is especially important to periodically test and exercise the entire system. That means each capability: self-protection monitoring, monitoring, reporting, and assessment, decontamination, and shelter monitoring should be exercised and personnel retrained as needed. Are you familiar with your jurisdiction's radiological protection system? Let's take a few minutes to review the status of your own community's radiological protection capabilities. Starting on page 6 in the student manual is a series of questions about your local RPS. Please read the questions carefully and write your answers on that page. Stop the tape while you complete this activity. When you have answered all the questions, restart the tape. Now that we have reviewed the radiological protection system, let's talk about the basic radiological concepts, vocabulary, and units of measurement that provide a sound technical basis for understanding radiation protection concepts. Everything in the world is made up of extremely small particles called atoms. The atom shown here is a normal atom of helium gas. The nucleus consists of 2 positively charged protons and 2 neutral particles called neutrons. Electrons, which are the lightest of the 3 basic particles, carry a negative charge exactly opposite to that of protons. Electrons are located in shells or orbits around the nucleus. Note the 2 numbers to the left of the abbreviation He for helium. The 4 represents the number of nucleons, protons and neutrons, in the nucleus. This is called the mass number. The 2 represents the number of protons in the nucleus, or the atomic number. The number of protons in the atom determines the element. Atoms are classified by their chemical properties, which means how they react with other atoms. The chemical properties are determined primarily by the electrons in the outer shells. Any agent that changes the structure or number of electrons in an atom changes its chemical properties. Radiation is one such agent. These chemical changes account for many of the biological effects caused by radiation. There is a precarious balance of forces in the nucleus of an atom. Any change in the number, configuration, or energy of the nucleons can upset this balance in the nucleus and cause it to become unstable. However, atoms that are unstable will not remain so indefinitely. Eventually, the nucleus will rearrange itself to achieve a more stable condition, ejecting nucleons and/or energy in the process. Radioactivity is the process by which unstable atoms make adjustments to become more stable. At first, the adjustment is an internal change, but as the process continues, it results in the ejection of a particle and energy. This is called disintegration, or decay, but that does not mean that the atom eventually will vanish. The number of atoms in a sample that disintegrate in a given unit of time is a measure of the radioactivity of that sample. 37 billion disintegrations per second equals 1 curie, written as capital C small I. The curie is the traditional unit of radioactivity. The international unit of radioactivity is the becquerel, written as capital B small q. 1 becquerel equals 1 disintegration per second. Every kind of radioactive material decays at a different rate. That rate is called its half-life. The half-life tells us how long it will take that substance to lose 1/2 of its activity by radioactive decay. A material with a short half-life may be decaying very quickly and emitting high levels of radiation. A material with a long half-life is decaying at a slower rate and will produce lower levels of radiation. It is important to understand that the amount of radioactivity measured in curies or becquerels is related to both the amount of material and the half-life. This large box of radioactive material could produce the same exposure rate readings as the smaller box of a shorter half-life material. As a radiological monitor, you are concerned with how radiation may affect people and animals exposed to it. Let's take a closer look at the 3 most common ionizing radiations encountered: alpha, beta, and gamma. When an unstable atom ejects an alpha particle, it is essentially ejecting 2 protons and 2 neutrons. Because of the relatively heavy mass and positive charge of the alpha particle, it will not penetrate even the first layer of skin. Therefore, alpha radiation is primarily a hazard when emitted inside the body. A particle of beta radiation has the same mass and charge as an electron. An ejected beta, which is actually like an electron except that it originates in the nucleus, will travel a few meters in air, or it can penetrate the first few layers of skin. Therefore, beta is considered an external as well as an internal hazard. Gamma rays are not particles. They are pure energy and may be emitted from the nucleus during alpha or beta decay. Gamma rays move at the speed of light and travel great distances in air. The distances could be a few thousand yards to miles. Because of gamma's great penetrating power, it is an external hazard and is usually considered the primary radiation hazard to people. In general, radiations can be put into 2 major categories: ionizing and non-ionizing. Ionizing radiations discussed here are capable, directly or indirectly, of removing electrons from other atoms. Until this happens, many atoms are electrically neutral. That is, they have the same number of electrons as protons. This process of removing an electron, leaving 2 charged particles, the atom with a net positive charge, the free electron with a negative charge, is called ionization. Whenever alpha or beta radiations pass near an atom, the attractive or repulsive force between the radiations and the electrons in the atom cause ionization. Ionizing radiations include alpha, beta, gamma, and X-rays. When the ionization process occurs within a human, biological damage takes place because the atoms that make up the molecules of blood and the internal organs are affected. The ionization process also provides a way to detect the presence of the radiation and allows it to be measured. And every time ionization occurs, radiation gives up some of its energy and becomes less harmful. There are other radiations that are called non-ionizing and do not create ion pairs. They include microwave radiation, infrared radiation used in lamps to keep food warm in restaurants, and the radio frequency waves used in broadcasting. Now, let's take a few minutes to review this section on fundamentals of radiation. Please turn to the matching activity on page 8 in the student manual. Read the number descriptions in the left column and then look for the correct term in the right column. Write the letter of the correct term in the space provided next to each numbered item. If you want to check your answers, turn to page 14 in the student manual. Stop the tape while you complete the activity and restart it when you are finished. The next section of this module will examine the 2 types of actions that are most important in protecting yourself, other emergency workers, and the general public from the harmful effects of radiation. Exposure control actions limit the exposure to people from radiation. Contamination control measures prevent the spread of radioactive materials. Let's begin with the general methods used for exposure control. Time is a critical factor for limiting exposure. It is important to organize your response effort before entering the radiation area and to work as quickly as possible. In rare instances of prolonged operations, the time any one responder spends in a high radiation area can be minimized by alternating the response personnel. In an airborne radiation environment where sheltering is necessary, the passive use of time is important. That means people should stay in shelter until the outside radiation exposure rate has decreased to acceptable levels. There is one very important exception to this advice about minimizing time in a radiation environment. When an incident requires immediate life-saving first aid, be sure priority is given to the required life-saving care first. Then consider exposure control of the patient. Distance is another factor that can be used to control radiation exposure. Just moving people away from the radiation source will reduce the risk, and the further the better. This is where the inverse square law is applicable. The exposure rate decreases as the distance from a point source of radiation increases. This occurs at a greater than 1-to-1 relationship. In this example, you can see that the exposure rate at 1 foot is 144 milliroentgens per hour. By doubling the distance from the source, the exposure rate is 1/4 of what it was at 1 foot. Remember that the mathematical aspect of the inverse square law does not apply in an airborne radiation environment, but it is still beneficial to move as far away from the outside walls of a shelter as possible. A final word about using distance as an exposure control method. Life-saving first aid takes priority over moving a severely injured person to reduce exposure control. As was previously explained, take care of life-threatening injuries first, then worry about moving the patient. In addition to time and distance, shielding is the basis for a third exposure control method. The shielding principle is very simple and applies to any radiation environment. The more material you can put between yourself and the radiation, the less exposure you will receive. The denser the material, the greater the protection. Shielding material can be barrels, boards, vehicles, dirt, or whatever else is immediately available. If constructing a shield takes a lot of time, personnel should be rotated to avoid prolonged exposure. Time, distance, and shielding, the three components of exposure control. Remember to apply these principles whenever your job takes you into a hazardous radiation environment. Let's take a few minutes to reinforce these concepts by completing an activity in the student manual. On page 9, you will find a small chart that indicates the 3 types of radiation and several types of radiation protection. Please place a check under the methods that are effective in protecting from the types of radiation listed in the left column. Hopefully, you will be able to complete the assignment without any difficulty. You may check your answers by referring to the school solution on page 15 of the student manual. Remember to stop the tape while you complete the activity and restart when you are finished. We know how to reduce exposure to radiation. How do we prevent radioactive contamination from spreading and creating additional problems? Contamination control is as important as exposure control in reducing harmful effects of radiation. However, contamination control requires an efficient system and attention to detail to keep track of contamination and prevent it from leaving a specific area. There are 2 types of contamination control: anti-contamination and decontamination. By taking proper anti-contamination precautions, you can greatly reduce the need for decontamination of equipment and personnel necessary after a peacetime radiological incident. Anti-contamination methods include use of minimum equipment and expendable material such as paper or plastic around or under equipment, protective clothing, and respirators. In an airborne environment where protective clothing would not be available to all affected, personal clothing serves an anti-contamination function. Although protective or personal clothing provides no protection from direct exposure to gamma radiation, It can prevent unwanted contamination because it can be brushed off or removed. In any situation where radioactive particles are airborne, some mouth and nasal covering should be worn to prevent inhalation or ingestion. Decontamination minimizes the further spread of contamination. As a radiological monitor, decontamination may not be one of your responsibilities, but it will be helpful if you understand the general operations. Let's first consider decontamination of uninjured personnel who have been monitored and found to have some amount of radioactive contamination. First, the clothes are removed, placed in a plastic bag marked radioactive, and held for proper disposal. A soft cloth is then used to decontaminate the skin, being careful not to abrade it. Liberal amounts of soap and water are used to wash particles from the hair. You should avoid getting suds in the eyes, ears, nose, and mouth. The hair should be washed several times before drying. The individual should be monitored again. If contamination is still detected, the washing process should be repeated. If contamination persists, health authorities can provide recommendations. For injured people, care of injuries is more important than decontamination. Once life-saving first aid has been carried out, the extent of decontamination that can be performed will be determined based on the severity of injuries and the amount of contamination. If decontamination is indicated, the first priorities are to prevent further injury and prevent internal contamination through wounds. Again, the first step is to remove and bag the patient's clothing. Then the patient should be carefully wrapped in a blanket for transport to the hospital. This will contain any contamination that might still be on the patient. Medical professionals at the hospital will carry out any additional decontamination procedures. If equipment has been contaminated, it too will need decontamination. This can be done as a post-emergency operation using well-thought-out procedures. Guidance can be obtained from your state radiation authority. What does your jurisdiction's standard operating procedure for radiation accidents say about protective actions? Please turn to page 10 in the student manual. At the top of the page are 3 questions about radiation protection procedures. Page 11 presents a hypothetical radiation accident situation and asks what protective action should be taken. Please read and answer all of the questions on the page. A suggested response to the hypothetical problem starts on page 15. Pause the tape while you complete your work and then resume viewing. If you have any questions about your community's procedures for protective actions, ask a member of the Radiological response team. The last section of this module deals with radiological hazard assessment. As a radiological monitor, your first task upon arriving at a radiation accident site is to evaluate the radiation hazard through monitoring and assessment. With all of the different types and quantities of radioactive material shipped by truck, rail, air, and sea, you might wonder how a radiological monitor can assess the wide spectrum of radiation hazards. Several sources of information are available. Actual monitoring with radiation detection instruments is one. In addition, all radioactive material shipments considered even slightly hazardous must follow certain shipping regulations. A great deal of hazard assessment information can be obtained from the packaging, labeling, placarding, and shipping papers required by the Department of Transportation and the Nuclear Regulatory Commission. This section will review those important sources of information. Department of Transportation, or DOT, packaging regulations identify 4 general packaging categories: packaging for limited quantity materials, Type A packaging, packaging for low specific activity, or LSA materials, and Type B packaging. Materials packed in limited quantity packaging have extremely low quantities of radiation per package and do not require outside markings. However, strong, tight industrial packaging that assures no loss of contents under normal transportation conditions must be used. The potential radiation hazard from such shipments is very low. If the packages were destroyed in an accident, measurable amounts of radiation might be found, but the radiation would pose no significant threat to public health or safety. The intent of Type A packages is to maintain their integrity during normal handling and shipping conditions. The regulations specify the quantity of each radionuclide that can be shipped in a Type A container. As a preliminary hazard assessment, if only Type A containers are involved, it may be deduced that there is little radiological hazard, because regulations permit only small amounts of radioactivity in these containers. Low specific activity, or LSA packaging, contain materials in which radioactivity is uniformly distributed in a large amount of non-radioactive material, or non-radioactive items with surfaces slightly contaminated with radioactive materials. Gloves used by medical and laboratory personnel involved in therapy or research would be an example. Risks would be minimal if LSA material was dispersed in an accident. When LSA materials are transported with other commodities, they must be contained in Type A packages. LSA materials totaling less than Type A quantities per package and shipped with no other commodities only need to meet the strong tight criteria for limited quantity packaging. Type B packages can be used to ship greater amounts of radioactive material than allowed in Type A. Type B packages are designed to contain contents and not yield increased exposure rates in the event of a severe accident. This Type B shipping container is called a spent fuel shipping cask. It is designed specially for shipping highly radioactive spent fuel from a nuclear reactor. The casks used to ship spent fuel are far stronger than other packages and can withstand 90 minutes in burning jet fuel and severe impact without being breached. In addition to the outward physical appearance of the package itself, the packaging label is another clue that can be used in assessment of the radiological hazard. Labels are found on two opposite sides of the package, not top and bottom. The label for a specific container depends on the exposure rates measured outside that package. The purpose of labeling is to inform anyone in contact with or near the package of its external radiation hazard and, in some cases, its contents. The regulations for external exposure rates near these packages are defined in terms of millirem per hour, usually seen as mrem/hour. Your CD instruments measure in milliröntgen per hour, or mr/hour. But for our purposes, we can assume that millirem per hour and milliröntgen per hour are equivalent. We will review these units of measure further in Module 3. Let's look at the various types of labels you may encounter. This label, called a radioactive white 1 label, is placed on packages of radioactive materials that have exposure rates less than 0.5 millirem per hour or milliröntgen per hour on any outer surface of the container. Because this is considered a very low hazard, there are no regulations specifying the number of radioactive white 1 packages on a carrier. If the exposure rate on the surface of the container exceeds 0.5 millirem per hour, but is less than 50 millirem per hour, and does not exceed 1 millirem per hour 1 meter away, a radioactive yellow 2 label would be applied. Containers with still higher readings are marked with radioactive yellow 3 labels. These packages may have exposure rates up to 200 millirem per hour on surface contact and 10 millirem per hour at 1 meter. The radioactive 3 label also is used for fissile class 3 materials, regardless of the measured radiation levels. Fissile materials are radioactive materials that could sustain a chain reaction. Other questions about the contents of the container can be answered from these labels. What is in the package? What is the contained activity? How high might the exposure rate be 1 meter from the surface of this container? The answers are all on this label. The container holds 0.2 curies of cesium-137. A reading taken at 1 meter away from the surface should not exceed 0.5 millirem per hour, as indicated by the transport index. Except in the case of fissile materials, the transport index is the highest exposure rate reading 1 meter from that package. This transport index is used to limit the total amount of exposure from radioactive material shipped on one carrier. By regulation, the total of all the transport indices on one carrier should not exceed 50. As you review the 3 labels, Notice that radioactive white 1 does not have a block for transport index. Remember, there is no limit to the number of these packages that can be shipped on one carrier, because almost no radiation exposure is received from these packages. The most outward indication of radioactive materials on a truck or train are the radioactive warning placards on all sides of the vehicle. Only vehicles carrying one or more packages with the radioactive yellow 3 label or LSA material must be placarded. Detection of radiation when monitoring the outside of a vehicle is not unusual. However, there are regulated limits to prevent serious exposure to persons outside the vehicle. The allowable external exposure rate limits depend on whether the vehicle carries only radioactive materials. These are called exclusive use vehicles. Non-exclusive use vehicles contain non-radioactive as well as radioactive materials. For a non-exclusive use vehicle, the exposure rate limit anywhere on the vehicle's surface is 200 millirem per hour. 1 meter from this vehicle, the exposure rate must not exceed 10 millirem per hour. For exclusive use vehicles, the limits are a little different. On contact, the limit is the same, 200 millirem per hour. But 10 millirem per hour is allowed as far as 2 meters away. Therefore, as you assess the radiological hazard in an accident involving a placarded vehicle, a reading at 2 meters away does not necessarily mean that packaging has been breached. In an exclusive use vehicle, exposure rates in the driving cab must not exceed 2 millirem per hour. In some cases, the shipping vehicle may be so badly damaged that the radioactive placards are not visible. Another clue to the possible hazard is the shipping papers. As with all hazardous material shipments, vehicles transporting radioactive materials must carry papers that properly identify the materials and specify associated quantities and hazards. The shipping papers, also called the bill of lading, air bill, or cargo manifest, must contain specific information for radioactive materials, including the proper shipping name, the proper hazard classification of the material, the 4-digit hazardous materials identification number, total quantity by weight, volume, or where appropriate, simply radioactivity, the name of the radionuclides, a description of the chemical form if not a special form, the activity in curies, milli or microcuries, or becquerels, the type of labels applied to each package, the transport index assigned to each package bearing radioactive yellow 2 or 3 labels, and any other information specified by DOT regulations. The location of the shipping papers depends on the type of vehicle. If an accident involves a truck, look in the cab. In an airplane, search the flight deck. On a ship, look in the bridge. And on a train, the shipping paper should be located in the caboose. By reading these shipping papers, you will be able to assess the possible risk without actually observing the cargo. Unless adverse conditions prohibit it, obtain these papers before calling for assistance so that you can provide needed information. If these papers are not available, as in the event of fire, any details about the vehicle, such as license number or other markings, will be helpful for identification purposes. Hazard assessment is an important part of response to any accident involving radioactive materials. To review and apply the concepts discussed in this section, please turn to page 12 in the student manual. The questions at the top of the page apply to your experience in assessing radiological hazards. The second part asks you to assess a hypothetical radiation accident situation. Suggested responses to the hazard assessment questions are found on pages 17 and 18 of the student manual. Pause the tape while you work. Resume viewing the tape when you have answered the questions. With thorough knowledge of hazard assessment, the responder is better able to identify possible hazards and safely monitor the scene of a radiation accident. If the accident does involve a radiation hazard, the Department of Transportation's Emergency Response Guidebook recommends specific emergency actions. For example, uranium hexafluoride is assigned Guide number 66. If you have a copy of the guidebook, turn now to Guide 66. The emergency action list includes the following steps and precautions. Keep unnecessary people away. Isolate health hazard and deny entry. Response actions may be performed prior to any radiation measurements. Stay upwind, keep out of low areas. Structural firefighters' protective clothing is not effective for these materials. Notify radiation authority of accident conditions. Detain uninjured persons, isolate equipment with suspected contamination, and delay cleanup until instruction of radiation authority. Call Chemtrack as soon as possible. The radiological monitor's role may be more involved in some radiation accidents and less in others. In accidents involving military nuclear materials, local responders are instructed only to save lives and establish an exclusion zone of at least 1,000 feet from the accident, and wait until proper authorities arrive. Local response to other types of radiation incidents, such as transportation accidents, may involve area and personnel monitoring in addition to administering life-saving first aid and limiting access. If you are familiar with the radiation hazards that are located in or pass through your community and have knowledge of the regulations and guidelines that apply to those hazards, you can be better prepared to respond to, assess, and recommend protective actions in the event of an emergency. Module 3. Once on the scene of a radiation accident and after initial assessment of the hazard, the radiological monitor may be asked to report on actual radiation levels. In order to provide accurate and timely information, the monitor must be able to operate and read the available radiation monitoring instruments. Because the most widely available instruments are the CDV series issued by FEMA, this module will focus on the role of the monitor in operating, reading, and caring for those instruments. To fully accomplish the module learning objectives listed on page 19 of the student manual, it is recommended that you have nearby 5 specific items of operational radiation monitoring equipment. 1. A CDV 700 survey meter. 2. A CDV 715 survey meter. 3. CDV 138 dosimeter. 4. CDV 742 dosimeter. And 5. CDV 750 dosimeter charger. As we have already reviewed, radiation causes biological effects by producing charged particles in matter. This same ionization effect allows us to detect and measure radiation, because the charged particles created when ionization occurs can be collected and counted by radiation detection equipment. There are 2 ways for a monitor to measure these events. One tells how fast charges are being produced, or simply the intensity of the radiation at some location at some point in time. This is called the exposure rate and is measured with a survey meter. If a person stays at that location for some length of time, then he or she will also need to know the total accumulated amount of radiation to which he or she was exposed, or the radiation exposure. This is measured with a dosimeter. It is helpful to compare the 2 types of radiological information with 2 of the meters in a car. A car's odometer measures the total distance the car has moved, just as a dosimeter measures the total accumulated radiation exposure. The dosimeter keeps track of your radiation exposure, even though the exposure rates may change as you move away from or closer to the source of radiation. Just as the speedometer measures how quickly a car is moving at a given time, the survey meter measures how quickly radiations are interacting with the detector. The survey meter tells you if radiation is present and the intensity of that radiation. Let's review what we know about the CD radiation monitoring instruments, starting with the survey meters. The 2 survey meters most used by radiological monitors are the CDV 700 and CDV 715. These will be referred to as the 700 and the 715. The detector on the 700 is a Geiger-Müller or GM tube. Recall that radiation produces charged particles when it interacts with matter. The GM tube is used to collect that charge and send it to the meter. When in the presence of certain types and amounts of radiation, the detector will cause the needle to move up the scale of the meter face. How far it moves depends on the amount of radiation interacting in the GM tube. There are two different units on the scale. We will concern ourselves with the top numbers that correspond to milliroentgens per hour, or MR per hour. What is the highest number on that scale? The highest number on the milliroentgen scale appears to be 0.5 milliroentgens per hour. But what if radiation levels are higher? The limit of detection can be increased by using another feature of the CDV-700. The range selector switch allows the instrument to measure not only 0.5 milliroentgens per hour, but also 5 milliroentgens per hour and even 50 milliroentgens per hour by simply changing the switch to a different multiplier. To take a reading on the meter, look at the needle's position on the scale and multiply it by the range multiplier. It is very important to continually practice reading the meter so you will be an expert when the need arises. When you are in a hurry, it will help to be efficient with the instruments. Let's try a few readings on the 700 as a review. Turn to page 21 in your student manual. 4 meter faces will be shown to you on your TV monitor. Record the meter reading, the range multiplier, and the correct exposure rate or explanation. You will need to leave the tape running while you complete this activity. If you would like to check your answers to that exercise, they can be found on page 26 of the student manual. Let's take a few minutes to review the operating characteristics of the 700. As was mentioned earlier, the instrument measures exposure rates in milliroentgen per hour. Its highest scale reading is the full scale needle deflection, 0.5, times the largest multiplier, 100, equaling 50 milliroentgen per hour. Remember that radiation must create a charge on the inside of the GM tube to be detected. What does this tell you about the types of radiations that can be detected by the 700? For one thing, the instrument cannot detect alpha or beta radiation with the probe closed, because neither alpha nor beta can penetrate the steel case. Second, beta can only be detected while the rotating section on the GM tube is opened, allowing beta particles to enter the window. The 700 is calibrated to measure only gamma radiation, so opening the probe window simply allows us to detect both gamma and beta radiation. There is a modified version of the 700 designed to detect the presence of alpha radiation in addition to beta and gamma. On this 700M, the GM tube is open on the end except for a thin mylar covering. This allows for the detection of alpha because the alpha particles can pass through the mylar. The 700M also is calibrated for gamma, and therefore will detect rather than measure the presence of alpha and beta. The 700 is primarily used for monitoring where the exposure rates are not likely to exceed 50 milliröntgen per hour. That would include most transportation accidents involving the shipment of radioactive materials, spills or accidents involving radiopharmaceuticals or medical radionuclides in hospitals and labs, and some incidents involving releases from fixed nuclear facilities. Don't forget that the 700 is equipped with headphones. They allow you to check for the presence of radiation without looking at the meter face. This is very helpful when monitoring personnel for contamination. Now, let's prepare this instrument for use. The first step is to install the batteries. Remember to shut the meter off before installing batteries, or you could receive a shock. Once the batteries are in place, you must perform an operational check. Turn the range selector switch to ×10 and wait 30 seconds to warm up. Next, open the beta window and place it over the check source on the side of the meter case. On the ×10 range, the reading should be halfway up the meter face scale. Your reading may be somewhat lower due to the age of the sources. A reading on this scale indicates that the batteries are operating and that on the ×10 scale, the meter is responding properly to the radiation. There is one additional test to perform. Turn the range selector switch to ×1. The ×1 range is more sensitive to radiation, causing a higher reading on the scale. With the range switch on ×1 and the beta window still open, perform the same check. This should result in a reading off the scale, which indicates that the ×1 range is responding, though not necessarily accurate. If you have a CDV 700 survey meter, this is a good time to practice your operational check. On page 21 of the student manual, you will find a list of the steps to follow. Pause the tape while you perform the operational check. Resume viewing the tape when you are finished. Having reviewed the characteristics and uses of the 700, let's look at the 715, which is the higher level radiation survey meter. Like the 700, the 715 is able to measure radiation on several different ranges by rotating the range selector switch. This detector has 4 scale multipliers, ×100, ×10, ×1, and ×0.1. The ×0.1 range allows this meter to read exposure rates as low as 0.05 Röntgen per hour, which is the same as 50 milliröntgen per hour, the highest reading on the 700. The 715 picks up higher level readings where the capability of the 700 is exceeded. Note that the 715 measures in units of Röntgen per hour instead of milliröntgen per hour. The 715 is a high-range survey meter, and the 700 is a low-range survey meter. The procedure for reading the 715 is the same as for the 700. Simply observe the needle position on the scale and multiply by the range multiplier. What will be the maximum reading on the 715? The maximum reading is 500 Röntgen per hour. Now, try a few readings on your own. Turn to page 22 in your student manual. 4 meter faces will be shown to you on your TV monitor. Record the meter reading, the range multiplier, and the correct exposure rate or explanation. If you would like to check your answers, they can be found on page 27. This is the inside of the 715. The radiation detector is a can-like component called an ionization chamber. What types of radiation do you think it can detect? It can detect gamma and X-ray radiation. The outer wall of the meter and of the ionization chamber are too dense for beta or alpha to penetrate. When would the 715 be used by a radiological monitor? This instrument can be used in incidents when exposure rates exceed those measurable with the 700. Let's look at some other characteristics of the 715. It measures gamma exposure to 500 roentgens per hour. The accuracy of this instrument for most gamma rays is plus or minus 30%. It is not affected by normal weather conditions. It requires a 15-second response time. And a new battery should last for about 150 hours of continuous use. The 715's only significant limitation is its inability to detect any radiation other than gamma or X-rays. Now let's review the operational check of the 715. This instrument requires only one battery. Remember to observe the polarity and be careful not to touch the circuit boards, since oil and moisture from your hands may damage them. Now the 715 is ready for an operational check. First, turn the selector switch to 0 and wait about 2 minutes for the survey meter to warm up. After the warm-up, with the switch still on 0, adjust the needle's position with the knob to the left of the handle until it is located over the 0 on the meter face. Zeroing the meter is the way you ensure the acceptance of readings during an incident. The 715 must be zeroed every time you intend to use it. When zeroing the survey meter, the detector does not respond to radiation, so it can be done even in a radiation area. If the needle does not respond when you turn this knob, replace the battery, clean the battery contacts, and try again. If there still is no response and the battery is good, then replace the instrument. Once the survey meter is zeroed, hold the selector switch to the circuit check position. If you do not hold the switch in this position, it will spring off. A needle deflection to or near the red area marked circuit check should be observed. If the needle does not move to about the 3 on the meter face, either the batteries or the instrument are defective. In this case, replace the battery and clean the battery contacts. Repeat the warm-up, zero adjustment, and circuit check. The circuit check also can be performed in a radiation field. Once the survey meter has passed the circuit check, test the operation of each range by slowly rotating the switch to each position and waiting to observe the meter deflection. When you are not in a radiation environment, the needle should not move further than 3 of the smallest increments upscale when the range selector is on the times 100, times 10, or times 1 scales. When on the times 0.1 scale, the needle should not move up further than 6 of the smallest increments. If the needle deflection is greater, you may be able to adjust the instrument by leaving it on for up to 16 hours on the 0 position. If this does not correct the problem, then the meter should be returned to your local emergency management office for repair or replacement. If you have a 715, this is a good time to practice your operational check. On page 22 of the student manual, you will find a list of the steps to follow. Pause the tape while you perform the operational check. Resume viewing the tape when you are finished. Survey meters determine the intensity of gamma radiation at any given location at a particular time. When conducting a radiation survey, you may move to many different locations where the radiation levels vary significantly. You must be able to keep track of your total exposure to radiation during a monitoring operation. The type of instrument that measures total exposure is called a dosimeter. The dosimeter keeps track of the total charge created by radiation interactions. To operate the dosimeter, you create an initial charge by zeroing it with a dosimeter charger. As radiations interact within the dosimeter, the charge is reduced and a reading is accumulated. The dosimeter can accumulate a reading corresponding to the amount of radiation it was exposed to from the time it was zeroed to the time it is read. After an incident, always remember to read and record your radiation exposure before recharging or zeroing your dosimeter. The two commonly available dosimeters are the 138, which measures gamma exposure in milliroentgens, 0 to 200, and the 742, which measures gamma exposure in roentgens, 0 to 200. Note that these dosimeters only measure gamma exposure. The needle inside the dosimeter will move up the scale as gamma radiation interacts in the dosimeter. To prepare the dosimeter for use, the 750 charger must be used to bring the scale to 0 for a starting value. To prepare the charger, install one D-cell battery. With your fingers, a quarter, a screwdriver, or whatever will work, turn the large screw on the charger counterclockwise. Do this until the charger comes loose from the casing. Install the battery according to the polarity marked. Put the charger back together, and it is ready for use. To charge a dosimeter, you must first remove the cap from the charging contact in the top left corner of the charger. Hold the dosimeter by the end with the pocket clip and press the other end of the dosimeter onto the charging contact. If the battery is installed properly, the dosimeter scale will be visible through the charger light. Now turn the knob on the right corner of the charger while keeping a firm contact between the dosimeter and charger. Do this until you can make the dosimeter needle read 0, or as close to 0 as possible. You need a light source to read a dosimeter. This can be normal indoor lighting, a flashlight, or even a candle. You also can, if necessary, take apart the charger, depress the light contact, and use the light bulb. Do not try to read the dosimeter by using the charging post. You could easily press too hard and lose your reading. Always hold the dosimeter so that the scale is level and the units of roentgens or milliroentgens are right side up. The dosimeter needle will drift, giving an inaccurate reading if held any other way. If you have access to a charger and dosimeter, it is a good idea to pause the videotape and zero a dosimeter for yourself. Then resume viewing the tape. There might be instances where no survey meter is available to determine exposure rate. Think back to our earlier analogy comparing the survey meter and dosimeter with the speedometer and odometer in a car. How would you estimate your speed if the speedometer was broken but the odometer still worked? First, you would measure the distance using the odometer during some time interval, and then divide distance by time to determine an average speed over that time period. In a similar calculation, exposure rate can be estimated with a dosimeter. You would zero a dosimeter and leave it in one location for an hour. The reading at the end of that hour would be the average exposure rate in the area during that time period. For example, if you left a dosimeter for 3 hours and it measured 90 roentgens, what would be the average exposure rate over that time? The average exposure rate would be 30 roentgens per hour. For practice in dosimeter readings and estimating exposure rates from total exposure, please turn now to page 23 in the student manual. 4 dosimeter faces will be shown on the monitor. Write down the correct readings on the chart in the student manual. After you have read the dosimeters and recorded your answers, pause the tape and complete the 2 problems on page 24. Correct answers to the dosimeter readings and problems may be found on pages 27 and 28 of the student manual. When you have completed the exercise, please resume viewing the tape. Dosimeter readings will not be accurate if the initial charge is leaking. Therefore, it is very important to test dosimeters by performing a leakage test to see how well the dosimeters hold their charge. Let's review the leakage test. The first step is to zero several dosimeters and place them in a radiation-free area for 4 days. At the end of the 4 days, the reading due to leakage should be less than 5% of the full-scale reading. For example, if the full-scale reading is 200, then 5% is 10. If the leakage is greater than 5%, that dosimeter should be set aside and marked as a leaking dosimeter. It is important to be familiar with this and other possible dosimeter problems. On page 25 of the student manual is a chart that reviews some common dosimeter difficulties and suggested solutions. This module has reviewed the preparation and operational checks for the 700 and 715 survey meters, the 138 and 742 dosimeters, and the 750 dosimeter charger. Although these are not the only radiological instruments used by first responders, they are the most readily available in many communities. State radiation authorities and health physicists may use other instruments at the scene of a radiation incident. If your jurisdiction owns other radiation detection instruments and expects you to use them, make sure to receive adequate training and practice on that equipment as well. Module 4. So far in this course, we have been concerned with reviewing the principles, concepts, and skills that are necessary to carry out the responsibilities of the radiological monitor. Now let's apply this knowledge to several possible radiation accident scenarios. In this section of the course, a series of radiological incidents will be described on this tape. Beginning on page 31 of the student manual, each scenario is provided, followed by related questions. You will be asked to use local or state standard operating procedures to analyze the events and determine your most appropriate responses as a radiological monitor. Your responses also should reflect the knowledge you have gained from the previous training and this course. If you find you are unable to answer some questions or feel you have not accurately or adequately responded, you may stop the videotape and rewind it to previous sections for review or refer to your student manual from the Fundamentals course for radiological monitors. Another option is to call a radiological response team member. Scenario 1. Radiopharmaceutical transportation accident. The first scenario occurs in the pre-dawn hours of December 3rd. A radiopharmaceutical transporter was involved in an accident. Two vehicles collided on a rural stretch of Interstate Highway I-55 near Brookhaven, Mississippi. No one was injured in the accident, which was caused by driver error in the slow drizzling rain. The vehicles involved were a passenger car and a Suburban towing a utility trailer. Shipping papers indicated that the utility trailer contained 76 packages of assorted radiopharmaceuticals with relatively short half-lives and a technetium generator. Total activity was 55 curies. The technetium generator, a high-level gamma emitter, presented the greatest radiation hazard. The impact of the crash threw the contents of the trailer all along the highway. Of the 76 Type A packages, 30 had their outer packaging destroyed. 2 of the 30 packages had inner containers which failed, causing breach of containment. These 2 packages contained vials of iodine-131. The 2 vials were ejected from their packaging and broken, with resulting contamination of the highway and shoulder. The technetium generator was found in the middle of the highway and had not been breached. Please turn to page 32 in the student manual and answer the application questions. Pause the videotape while you work and resume viewing after you have answered the questions. Scenario 2. Industrial radiography accident. In the second scenario, an industrial radiographer uses a strong gamma source to check for hidden flaws in pipe wells. The process for taking a picture or radiogram is similar to that of a chest X-ray. The film is attached to the outside of the pipe, and the high-level radioactive source is pulled through the pipe with an attached cable or wire. A guide tube gets the radioactive material out of its shielding or camera and back inside after the job is done. In this scenario, the industrial radiographer had trouble with the radiation source as he cranked it down the guide tube to the area to be radiographed. The exposed 120 Curie cobalt-60 source seemed to be stuck or blocked in the pipe. The guide tube, which is made of thin rubber, provided little shielding. While trying to solve the problem, the radiographer was hit on the head and knocked unconscious by falling pipe. Please answer the application questions on pages 33 and 34 in the student manual. Pause the videotape while you work and resume viewing after you have answered the questions. Scenario 3. Nuclear power plant accident. Scenario 3 occurs at the Acme nuclear power plant. After a series of equipment failures and human error at the plant, the coolant water in the reactor core decreased to the point that the fuel was no longer submerged in the water. Some of the fuel rods melted, releasing large quantities of radioactive material into the containment building. Following prescribed notification procedures, the plant upgraded the emergency notification levels throughout the crisis. At 1 p.m., the plant declared a general emergency, which meant that there was potential for breach of containment or radioactive releases expected to exceed acceptable levels off-site. Please turn to pages 35 and 36 in the student manual and answer the application questions on that page. Pause the videotape while you work and resume viewing after you have answered the questions. Scenario 4. Transuranic waste transportation accident. In our fourth scenario, 3 TruPac 2 containers of transuranic waste en route to the Waste Isolation Pilot Project facility in Carlsbad, New Mexico, were involved in an accident. Transuranic waste is contact-handled waste. It is the protective clothing, tools, rags, and other materials used when producing nuclear weapons. Because it is contaminated with plutonium and americium, giving off relatively high levels of radiation, it is packaged in a Type B container. The accident occurred on Interstate 25 near Colorado Springs, Colorado, when a Volkswagen and the tractor-trailer transporting the TruPac 2 containers collided. Injuries were sustained by persons in both vehicles. The driver of the tractor-trailer was rendered unconscious, and the alternate driver sustained a broken arm. The Transcom tracking device was damaged on impact, but the mobile phone was left intact. The Volkswagen caught fire, and one TruPac 2 container was punctured. Because plutonium and americium are alpha emitters, they may present significant internal radiation hazards if inhaled or ingested. At this time, please answer the application questions on pages 37 and 38 in the student manual. Pause the videotape while you work and resume viewing after you have answered the questions. Scenario 5. Terrorist threat. Scenario 5 occurred on November 1st when calls were made to the mayors and FBI offices of 3 U.S. cities. The callers threatened to detonate 1-kiloton nuclear weapons in each of the 3 cities if the incumbent president of the United States was reelected. If these nuclear detonations were to occur, there would be extensive destruction and loss of life in the target areas. Also, there could be disruption of goods and services across the country, and a significant fallout problem throughout the nation. Please answer the application questions on page 39 in the student manual. Pause the videotape while you work and resume viewing after you have answered the questions. After you have completed your responses to questions related to Scenario 5, you may wish to review the suggested responses to all 5 sets of questions. They are located in the summary at the end of Module 4, beginning on page 40. Pause the tape while you review and resume viewing when you are ready to continue. Module 5. We have come to the last module of this course. This concluding module is intended to provide a summary of course highlights and to help you determine whether your individual learning objectives were fulfilled. Now that you have completed this course, we hope that you are proficient at certain skills. Please follow along on page 48 of the student manual and check off the tasks you can perform. Categorize radiation hazards in terms of potential scope and health hazard. Identify critical elements of the radiological protection system, basic radiation protection principles, basic concepts of radiological hazard assessment, monitoring techniques, and protective actions. Given a list of characteristics, identify types of radiation. Describe how to perform operational checks of the CDV 700 and CDV 715 survey meters. List the correct steps to follow in zeroing and charging the CDV 742 and CDV 138 dosimeters. Convert survey meter readings to exposure rates. Determine possible solutions to problems with radiation survey meters. Determine radiation exposures indicated on ion chamber dosimeters. Analyze radiological incidents and determine appropriate radiological monitoring response. Let's take just a few minutes to re-examine the life-saving principles we have discussed. Exposure to radiation means that you have been in the presence of gamma radiation. As soon as you walk away from the radiation source, the exposure is over. Contamination from radiation means you have either ingested, inhaled, or have nuclides emitting alpha, beta, or gamma radiation on your person. The radiation is on or within your body and goes where you go. There are several protective actions you can take to reduce the risk of radiation exposure. The less time you spend in a radiation environment, the lower your exposure will be. The more distance you can put between yourself and the radiation source, the less exposure you will receive. The more dense the material you put between yourself and the radiation, the lower your exposure will be. Dosimeters measure your total accumulated exposure to a radiation source, much the way an odometer works on a car. Survey meters measure exposure rate, or the intensity of the radiation field. They tell you how much radiation you would be exposed to if you stayed in a particular place for an hour, similar to a car speedometer telling speed per hour. It is important to remain familiar with your CDV instruments. Practice performing operation checks and take practice readings using low-level check sources. Know how to use the instruments when you need them. Finally, remember that you have a radiological protection system to rely upon. Become familiar with the radiological annex of your emergency operations plan and stay in contact with radiological response team members. Participate in exercises whenever possible. And in the future, participate in training opportunities whenever available.